Yeah, Kaito. A very good morning to you all.
Good morning, sir.
Good morning, teacher.
How was your weekend?
Good morning, sir.
I've sent you some more numbers you look at, underline of action and moments. And that topic, we finalized it last week. I did not get any inbox challenges. Either learners did not solve at all, or they solved all of them and they passed them. That answer is best answered by you guys. So today I want us to introduce something else. Still under mechanics. Yes, please.
Can't you first look at teacher? Can't you first look at the last number we did before you introduced the new topic?
The last number, was it an assignment or the question we did?
No, we did not do it. It was an assignment.
But you never sent it. Why did you? You know those numbers, you have to send them before the class comes. Which number was it over? I can find it. Because even the book is different. What was it about?
Teacher, the part B was like if the forces are replaced by a single force at the origin and a couple, determine the moment and direction of the couple.
So the second part failed. Eh?
Yes.
ABC is a rectangle in which AB is 5. Is that the number?
Yes.
Okay. Forces of 2 newtons, 4 newtons, 3 newtons, 11 newtons act along AB, BC, DC, DA, respectively. Taking AB and AD as X, Y axes. So you prepare this weekend, you might have the test of paper 2. I'm trying to finalize the setting, but I'm going to mix my work. I'm mixing mechanics. You're going to have start, you're going to have numerical methods. And we intend to have at least a maximum of 3 numbers from each section. Okay, numerical, they might be 2, but these other ones, they can be 3. You might have 3 numbers here in mechanics, 3 numbers in start and probability. You may have 2 numbers in, that is 8. So please prepare. You do the numbers, I think, on Saturday and Sunday. And by Monday, we should be able to hand in. Okay? I'd forgotten to make the announcement. Remember, I told you earlier this month, we are going to have a test. So ready ourselves. Okay, let me go back to the number. The lady has asked for assistance. So they have said this number has, if you label the triangle, we label it anti-clockwise, A, B, C, D. AB has a force of 2 newtons. BC has a force of 4 newtons, but with 3 meters. And then this one has 5 meters. We have DC has 3 newtons. And then lastly, we have DA at 11 newtons. I think that is it. They said, find the line of action of the resultant force, which I assume the resultant force can be got from the sum of X and sum of Y. If I place them in vector form, I will have 2, 0. If I use vectors, plus 0.4 plus 0 negative 11 plus 3.0. And when you finalize all this, the resultant force gives you a magnitude of 5, negative 7. Meaning the sum of forces in X is 5, while the sum of forces in Y is negative 7. Remember, Y is the same as also being given as capital Y. Then this one is called capital X. Then the moments, you take moments about A, you will have 4 times 5, because this 5, this 4 would be going anti-clockwise, then the 3 would be going clockwise. Minus 3 times 3 is the moment. So G becomes 20 minus 9, and the answer is 11 Newton meters. Where is it going? Anti-clockwise. I hope we all got those first parts. The lady who asked, did you get those parts?
Yes, teacher.
Okay. So therefore, remember the equation of the line of action is the sum of the moments minus x capital Y plus small y capital X is 0. So this gives us 11 minus x times negative 7 plus y times 5 is 0. Our equation of the line of action is y plus 7x plus 11 is 0, which is the equation.
5y.
Eh?
5y.
5y. Very good, thank you. So I trust maybe most of you, all of you got that, whoever was attentive and has been trying numbers. Now the question said, what did it say? If the forces are replaced by a single force at the origin and a couple, determine the moment and the direction of the couple. Sorry, someone wants to jet into my account. No. So we are saying if the forces at the origin are replaced by a single force. So our origin is assumed to be A. Remember, the origin comes from the coordinates and the axes X and Y. So if this is where our A is, okay, and we are replacing this A with a what? What have they said? Read the question there.
Like, if the forces are replaced by a single force at the origin and a couple, determine the moment and direction of the couple.
So remember up here we had a 7. The resultant up here was what? Was 7 going downwards. Why is it 7? It is because the sum of forces, we had 11 and 4. When you sum them together, you get negative 7, which acts in the negative y-axis. So it would be going where? Downwards. Then on the horizontal, we have 5. But this 5, if you to resolve, it would be going anti-clockwise. If you were to assume that C was here, but you don't have actually, and you are to assume that we had here what? D. Okay. Then they have said if you are reducing it to a single force, now we can assume. Let me see what the question says. Where is the question? If I assume P is a force, I assume P is the single force that reduces the system to a couple. What do we know about a couple? A couple is, who recalls what the definition of a couple is? Who recalls?
The resultant of the forces.
The resultant of the forces is 0, not? Yes?
Yes, it's 0.
Now, if in the vertical 7 is the resultant, then it means there should be another 7 up here to counterbalance this 7 Newton to get 0 in the vertical. Is that clear? If there is a 5 in the horizontal as the resultant, there should be another 5 counterbalancing that 5
Excuse
in the
me, teacher.
horizontal. Yes, please.
Excuse me, teacher. Which question are we on? I
The
came
question-
late here.
Yeah, the question.
Yes.
Over which question was that one, Madam? The question, which one? Which question was it? The question I gave as assignment, the first one in class before I left. Leave alone the ones I've sent today. The ones I've sent today, you do them later. But the one I gave it as I was doing them, but then I left it for you to finish it.
Okay, teacher, I have known.
You've seen ABCD is a rectangle. Yeah. Okay, guys, have you understood what I've said? Let me come again. We have initially seen that if you sum up the 3 and the 2, they're acting in the same direction. They give you what? 5 as the resultant in the x-axis or in the horizontal. In the vertical, we have 11 going downwards, 4 going up. The resultant in the vertical is -7, meaning it's going down. To reduce to a couple, the vertical component must be 0, even the horizontal component must be 0, which means the entire resultant force must give us what? 0. So to reduce to a couple, the upward component here should be a 7 also, so that when you subtract the 2, you get 0. Then if this one has a 5, the resultant component on the opposite side also should be 5. Whereby if I merge these 5 and this 7 I've introduced, I'll get this one. Let me use another color. If I merge this 7 and this 5 I've introduced, I'm going to realize the following. This will become our 7 newtons. So if that is the case, it means my P is going to be equal to, the magnitude of that P will be the square root of 5 squared plus 7 squared. Okay, and thus the P will give us 25 plus 49 under the square root. This will give us 74 under the root newtons as magnitude of P. Now, the direction also of P is required. Or the direction of P is here, whereby tan alpha will be equal to 7/5, and alpha will be tan inverse of 7/5. What angle do you get?
$54.46.
54.46. So remember the moment about N was already found, was 11 Newton meters anti-what? Anti-clockwise. So in this sense, the direction of the moment of the couple, the direction of the moment of the couple about A is going to be because the direction has gone this side, you see that it is going west. If I put a compass here, west 54.46 degrees going where? North. And its magnitude is 11 Newton meters anti-clockwise. Yeah, because the question was saying, determine the moment and the direction. So the moment was already got about A. And the direction is what we have found using that assumption that if they are to reduce to a couple, what would happen? In that sense, you would see that you have the direction as west 54.4 degrees north, or you can confirm using north 90 minus 54.4, 6 degrees going where? Westwards. Hence the solution. Okay, so you can have that screenshot. You have a lot of other numbers. I gave you like 5 of them. They're not so many, but visit all questions in the question bank. Someone who has a question bank, post all the numbers, please, concerning moments and line of action. Not center of gravity, but line of action. So post them for people to see how relevant this is. I have my seminar and thingy book, but I don't have enough time to open the seminars, all the questions, and take screenshots. But those of Gombe and Narusunsa, if possible, when you come back to school, all of you will be able to purchase the book. It is full of revision mock papers and what? And seminars. Looks like this was compiled by myself. I don't know if you can see this. So it has quite a number of pages, as you see. It's quite a big. All these are just numbers for people to handle. So there are quite very many, including paper 1 mathematics and paper 2. But those around Kampala, if you have some money, if you have the money for the book, which is 30,000, you can arrange, and I deliver the book with a border guy. You pay him, I think, 5K. Within Kampala and Wachiso, those ones can access, apart from those very far away. Because we are turning towards, by the time we come to next year to go to school, I trust we shall be almost done with the syllabus. And if you keep the momentum you are at assured A's, unless if you're not serious. But if you're serious, trust me, you'll never regret this time. Yes, lady, you are saying something.
Just saying thank you.
You're welcome. Okay, guys, with that main heading, new page, new page, elasticity. Elasticity.
Yeah.
Yes, please.
There was a number in understanding mechanics. It was number 11.
Now you hear this man bringing another. I'll handle it and send in the WhatsApp. You WhatsApp me the number. Because guys, if you don't send the numbers before the lesson, it inconveniences our program. That is why I always say, in case of any challenge, inbox me. But you don't. You mean you can't put for us on a bus to transport? Okay. Those on the bus, okay, I can also arrange for you if you pay. Okay. Yeah, guys, whoever has any other number concerning line of action, please visit my inbox. Also put it on the group so that when I give the solution, I'll come and confirm together with the group so that everyone can access the solution to the challenge. Okay? But please never wait again for numbers to reach this time. Always, if you have a challenge, post it. Sometimes I delay, but I still get back to the students. Yeah? Okay. Today we have to start elasticity, guys. We might need some 2 or 3 weeks for this. So we overdelay. Some of you might miss seeing my circular motion here. You might miss seeing my center of gravity. You might miss missing my simple harmonic motion. So we have some other 4 topics left in mechanics. We'll start there like 2. Actually, start there like we have only confidence interval. So we are still in normal distribution. After normal distribution, confidence interval, we are done. But for mechanics, there's still quite some many. And when I finish that, I'll just borrow some time. Then we do some pure math, which is pending, because you have a lot of sections also there which are pending. Now, elasticity. All of us have ever seen something which is elastic. If you have not, just go and get your boxer, because some of you might be putting on jeans, or go and get your knicker and then pull it to the side. You will see it is becoming elastic. Okay, maybe that is very fun. Get your shirt. My t-shirt is elastic. If I pull it, you see what happens. It elongates, then it goes back to my body. It means my t-shirt has elasticity in it. In physics, it is a physical property of matter that shows how bodies or matter does extend when a force has been applied on it. So when you look at the shirt, when I'm seated as you see me here now, yeah? Let me first close the share. Okay. Yeah, as you see me here now, fully, I think you can see me fully now. The t-shirt is not being affected. But if I pull it, it means my hand has put a force on the t-shirt. So one of the conditions that have to be there for elasticity to occur, there should be a force. A force that makes the body extend. A force that pulls the body. A force that causes the molecules of the material, which is elastic, to extend. Now, why does elasticity behave the way it behaves? Elasticity is in a form that, for example, if you have these elastic materials like rubber, most of these materials that are elastic, they either have rubber within in themselves. If you look at those boxers, I'm giving an example of a boxer because everyone has one. Even a knicker, girls, you also have one. And we have always put them on. And we know they're elastic. But if they get old, if you wear them to that maximum, and they get cut, there is a white rubber inside them. But I don't have a rubber band with me here. I would have showed you using the rubber band. But I had a mask. Where is my mask? I had an elastic mask. It was sold. Where are you? Okay. Now, that elastic rubber is made up of molecules which are coiled. The reason why rubber extends better than any other material that extends, it is because rubber, the molecules first uncoil, then again the molecules extend when a further force is applied. So that is how elasticity takes place in elastic materials. We have other elastic materials. For example, we have a spring. All of us have seen springs. If you have not seen one, you're lucky. Nowadays, there are no beds made of springs. You used to have decals of springs. A spring looks like this, those of us who have never seen one. That is what they call a spring. When you put a mass here, the spring will extend in this form. So it means the spring has extended. If initially it was here with a length L, not, then it has attained an extension E as a result of pulling it maybe down by force. This is an extension E. Some books call it an extension X. So about extension, all these are talking about, now who is saying boxer and knicker, very good example, because everyone has one. If you have, if you know your bedroom, you pick one which you've washed, check and see, is it elastic? Unless if you have one which has a belt, which I don't think any of you has ever had one of that kind. But anyway, I gave them as the best examples because I know everyone has one. But now, leave alone the examples. It means when you're putting on, you are applying mechanics because you extend it so that your leg fits through. When you're putting it on and then it reaches your waist, you release it, it comes and grabs your waist. When it grabs your waist, it behaves as an interlocking. So elasticity can provide items in terms of locking up items. Even these springs, they are put on doors, whereby if a door is opened, the spring pulls it back. They are put on doors, they are put on photoelectric doors. Sorry, those who don't offer physics, I'm over mentioning some physics here. Photoelectric doors are doors which open automatically. You go to a supermarket, a superior hotel, the door opens for you. You wonder. Don't over wonder. That is simple mechanics. There's just a spring within, and then there's some simple radiation that is being either covered by you, then it forces the door to open. So with those extensions, springs are applied in also very many other items. There are these chairs we sit on, office chairs, when they bounce, they have springs. There is a spring mattress. Have you heard of spring mattresses? Some people even say there is a water bed. Water bed, water spring bed. So they cause oscillations. So we need to understand the point of elasticity here, so that when we come to the point of simple harmonic motion, we shall be able to understand whatever comes next. Because it is very good to understand elasticity, then you proceed with simple harmonic motion. Reason being, simple harmonic motion also has extensions in it, which extensions come as a result of elastic material or elastic components. So these two mechanics sections are connected. So with that, you can consider.
Excuse me, teacher.
Yes, please.
My question.
Yeah.
Does any elastic object have as a line of action of the resultant force?
Does an
I'm saying
elastic
that-
material have a line of action of the resultant force?
Yes.
Is that what you're asking? Is that what you're asking?
Yes, teacher.
No,
Yes.
no. First, forget line of action now. We do not have lines of action here. But what I can say, maybe what you should understand is that there is a line that extension has to follow. If the extension was along a vertical line, like you're pulling this mass downwards with a weight mg, then this line should be followed. If it was a string on a horizontal, and that string is connected to a body, and the body is pulled this way, the body has to come back along that same line. But that line is not what we call the line of action. It's just that it follows the line of the force which is pulling it. Yeah. So consider strings that are elastic, that can be stretched. That can be stretched and regain their elasticity. After their stretching force has been removed. Now, when these particles have what we call a stretching force, sometimes the topic is written elasticity and then in brackets, Hooke's law. If the material is elastic, though we don't go into details of the curve, but the material can obey Hooke's law, then you have proportionality, then it becomes plastic, then it undergoes deformation, then it breaks if any other force is applied. But for us, we don't go in those details in mechanics math. In math mechanics, we stop at proportionality law, which is Hooke's law, whereby if the force is removed, we expect the material to go back to its original size. That is why when you see the gloves, most of you don't know gloves, but if you put on gloves, you see they fit your hand. If you remove them, they are small. If you put on a panty, you see it is now huge. When you remove it, it is very small. So it is because it extends when the force has been applied. When you remove the force, it goes back to its original shape and size. This is what we are saying, that when a material, which is elastic, has been stretched, it can regain their elasticity after the stretching force has been removed. So it means it is not losing its elasticity in this sense. But there's a possibility of losing it. If someone who is very big who is in senior 5 gets to put on an hand of a nursery kid, trust me, the kid won't be able to put on that hand anymore. Why? You are going to stretch it to maxima and you're going to remove its elasticity. Its tendency for it to recover its original length, shape and size, you're going to disorganize it and kill it. So in that sense, you will not be in position to regain the original shape and size. So therefore, if I look at this illustration, where I have 11 charts, what is happening? Are people chatting? Is it allowed? What is allowed? Winnie, it's a new topic in Sedeco. Hey, okay, yeah, it's off. He's offline. He's offline. In Sedeco, stop teasing. How is teasing? Come on, guys. We are in elasticity and you're talking like as if I will close the chats. Leave me muta. Okay. It's just nonsense. Anyway. And now when you write like that, now me, I tend to neglect the chats because I would think people are putting their nonsense. So mind what you put there. So if I stretch a material, maybe this is the material, and then I stretch it to a point C, whereby if this is point B, this is point A, and this is point C. Then if initially this was the original length L, and this is the extension E of the material. If AB is a string of natural length. Now, in this sense, when you hear natural length, what does it mean? Natural length is the original length. Natural length L is stretched to a point. Stretched to a point C. Then, from Hooke's law, tension is directly proportional to the extension. Now, in mathematics, we rarely state Hooke's law, but we can state it for just. Who can remind us what Hooke's law states? Anyone to recall what Hooke's law states from O level?
States that the extension of an elastic material is directly proportional to the applied force, provided the elastic limit is not exceeded.
Very good. Provided the elastic limit is not exceeded. Provided the elastic limit is not exceeded, comma, the force applied to an elastic material is directly proportional to the extension produced. Okay? The force is directly proportional to the extension produced, provided the elastic limit is not exceeded. So that is what Hooke's law states. So that is where this relationship comes from. Some books have it as F is directly proportional to E, or F is directly proportional to X. Now, in that sense, you will have either tension is equal to KE, or you will have force is equal to KX. All of them apply, and it works. But we can agree. Can we use T or can we use F? What do you want? We can use T, I think, because it is tension in strings and springs. So let's use T, and we use also X. Therefore, we shall conclude that T is always equal to KX, as per what the law has said. But K is what we call the force constant. Force constant of the string or spring or of the material, whereby the force constant K is given by lambda out of the original length L. Sometimes the original length L is called L naught, whereby now lambda is what we call the modulus of elasticity. Then L naught is what we call natural what? Natural length. Then X is what we can call the extension produced. And then the T is what we are going to call the force in the string or in the wire. Therefore, another expression can be deduced that T is equal to lambda X over L naught. This becomes also an expression for tension of an elastic material. So far, any question on that derivation? If no question, you can have an example using that equation. So example 1. A string of natural length. So now when they mention natural length, you know what they say. 3 meters has modulus of elasticity of 2 newtons. Fine. Yes, please.
Does T also represent the force? Are they the
Yeah,
same?
it is representing the force. We said we can use T as the force. Reason being, we are looking at strings and they experience tension in them. Strings and springs.
Okay, thank you.
Tension is there. Find the tension in the string when stretched by 33 centimeters. So that is our first example, illustration. Find the tension in the string when stretched by 33 centimeters. So the question says it is stretched by 33 centimeters. It means that is the extension. Okay? So if that is the extension, then also you have to work in SI units because you see already there is an SI unit of Newton. Eh? So the extension E, which is our X, is actually 33 centimeters out of 100. This becomes meters. They have given us the modulus of elasticity lambda, which is 2 newtons. They have also given us original length, which is natural length, which is 3 meters. Sometimes this natural length, where is it? Some books have it as A. So you might find the equation in this form, T is equal to lambda X out of A. Don't get worried. A is the natural what? Natural length. Therefore, because they're asking for the tension, which is equal to lambda over L naught times X, this will give us 2 times 0.33 divided by 3. By 3 once, by 3, 1, 1. So when you multiply, the tension becomes 0.22 newtons. Isn't it very lousy? I think it's very obvious, not so? But of course, you know, this is mechanics. It can be very lousy in the beginning, but as we grow big and we grow further, it becomes interesting. But we have to give you these welcoming examples so that people don't run away from the topic. Okay, Abdi has raised their hand. Yes, Abdi. Abdi, your hand is up. Abdi, you've gone to the chat where people were chatting from. You mean you can't put? Abdi, what have you said? Sir, I can unmute. You can't unmute. Oh, how? How come others can? No, you can unmute, man. Abdi, let me unmute you. Okay. Abdi, have you been unmuted? Abdi, even me, I can't unmute you. What's your problem?
So let her re-enter the lesson.
Yeah, you try to re-enter the lesson. Someone has suggested. Okay, let's proceed. I get another example as he comes back. This Hukasha is just coming now. They are going to see fireworks, those who are just coming in. We need a technician. What does that mean? For my example 2. An elastic string. That is why when we are dealing with the pulleys and items before which had the strings, the questions were set like this. In an inelastic string, they could tell you that the string was inelastic, meaning it couldn't extend. But now here, they will tell you the string is elastic. When they say it is elastic, Hooke's law has to come into play. An elastic string of natural length. An elastic string of natural length, 4 meters, and modulus 20 newtons is stretched. Find 1, the tension in the string when X is 40 centimeters. 2, the value of X when T is 4 newtons. Of course, here they are talking about X as the extension. This should have been stretched by X. Find the tension in the string. So remember, tension is got from modulus of elasticity divided by the original length times extension X. So the tension is going to be lambda is what? 20 divided by the original length, which is 4 meters, times the extension, which is 40 out of 100. By 40 here, 10. By 4 here once. Here you get by 10, 10. Reduce the 10 by this 2. Finally, the tension becomes what? 2 newtons without even using a calculator. Part 2, this is part 1. Part 2, the value of X when T is 4. So when T is 4, we shall have 4 is equal to lambda out of L naught times X. So if they want X, make X the subject. X will give us 4L naught out of lambda. You realize that it will be 4 times 4, divided by 20, and the answer is 16 out of 20. By 4, 4. By 4, 5. My x will become 0.8 meters. What does that mean? It means the first extension was 40 centimeters. The second one is 80 centimeters. There should be consistency in your answers. Reason being, it is the same string and the same modulus. So if it is the same string, that's why I said, if you're putting a t-shirt, the whole of it comes. But my trouser is not affected. If you have a kanzu or a dress, and you pull a kanzu from one side, the entire kanzu will come off, or will come off and pull the person. But now, it means that, check and see. If the force is small, we expect a small extension because they are directly proportional. If the force is big, we expect a bigger extension. So we are getting a big extension here. Is the force greater than the force we had before? Yes, actually it has doubled. Because of the consistency, because these occur on a straight line, or if you have the plotted on a graph, maybe in physics, that's where we can put more energy. Because the extension was 40, when the tension was 2, when the tension is doubled to 8, when tension is doubled to 4, even the extension will be doubled to 0.8. That is why the answer is correct and consistent. Tushime, your hand was up.
Why are you dividing by 100 in the 40?
To convert it to meters, it was centimeters.
Okay.
We there? Yes, please.
So what does modulus of elasticity mean?
What does modulus of elasticity mean? Modulus of elasticity, we have seen it comes from the other aspect, which I talked about as the constant of proportionality of the spring. So the modulus of elasticity is ideally the ratio. It's ideally the ratio I wrote it in this form. Where is it? Let me show you using an equation. Where is it before? We are getting the modulus of elasticity from here. The modulus of elasticity is what determines the strength of the material. The strength of the material is what determines the constant force one requires to have an impact on that material. Whereby if you do not reach that constant force, the material cannot get extended at all. So every material extends differently. That is why we are saying every material has a different force constant, every material has a different modulus of elasticity. The way the t-shirt extends is not the same way the boxer does. The way the knicker does is not the same way the bra will do. The way the rubber band does so is not the same way the gloves will do. The way any other thing that extends, will extend is not the way another one will extend. Why? Because they have different force constant as a result of having different moduli of elasticity. So modulus of elasticity is ideally a force which you require minimally, which that material tells you must have this amount of force. Without it, you cannot extend me. Guys, did you even know that metals also can extend? Do you know that? Metals, metal bars you see. We went to the factory in Jinja, which is called Steel what? Steel Rolling. There's a factory in Jinja, the only one in Uganda, which makes bars, iron, from raw materials, from magnetic iron, magnetic rocks of iron. They're extracted from, I think, Kasese. Then they are brought to Jinja as stones, but they are magnetic stones or magnetic rocks. Then those magnetic rocks are boiled in a furnace. Then they're put into molten state. Then they are cooled down. And then they form metals. But as they form metals, they are taken to the lab to test their strength. to test their modulus of elasticity. So they are pulled, they are extended, and they can be modeled into different shapes. So every material has such a constant. Your lesson is running so fast today. Why? Okay. We can also, those were elastic strings. Yes, please. Someone is saying something. Now, in elastic springs, a spring, the other one was string. This is now a spring, P, can either be stretched or compressed. When it is compressed, we talk of thrust rather than tension. So whenever you hear thrust, just know they are talking about a compression of the spring. If I don't have a spring around me, I would have showed you one. With time, I'll see how I can arrange one. I'll go to the lab and I think pick that. I'll go to school, I'll go to my students and pick some springs from there. Then you have an example on this. A spring of natural length 1.5 meters is compressed to a length of 1.2 meters. If the modulus of elasticity of the spring is 15 newtons, find the thrust in the spring. So you hear now they're saying find the thrust in the spring. They're asking you to find the compression in the spring. So initially, the spring has an original length, L, which is what? L naught, which is 1.5 meters. It is compressed to a length of, the new length, L prime, is equal to 1.2 meters. The extension is going to be 1.5 minus 1.2, which is going to be 0.3 meters as the compression. Sometimes remember we say this can be called what? X. The modulus of elasticity is 15 newtons. Find the thrust in the spring. They're asking you for the tension in the spring, which is going to be the tension or the thrust is got from lambda out of original length times the extension x. With that reason, we shall have T is equal to 15 out of 1.5 times 0.3. By 1.5 once, by 1.5 10. Tension is going to be 3 newtons, which is our compression. Okay.
Excuse me, teacher.
Yes, please.
Is the tension the same as compression?
Yeah. The expression we use is the same. It's just that you just need to understand that this time around we are compressing, the other time we are extending. But the expression we use to find them is the what? Is the same. Screenshot that. The next number is for the learners. Okay. Taking the screenshot. This one is yours. A superine of natural length.
Teacher, first take me back to the previous page. It's done.
Spring of natural length, 2 meters, and the modulus, 30 newtons, is compressed find the thrust in the spring when compressed to a length of 1.5 meters. That one, try it out very fast. If you've taken that screenshot, I want you to take this screenshot very fast. It is for your exercise. It is from Bostock. Take screenshot from question 3 to question 10. How do I remove these yellow parts? My God. I don't have the soft copy of Bostock just hanging freely. I have a library on my laptop, a soft copy library, so it's what I'm using, and I can't transfer this book directly to you. That's why I can't send it, but I'm going to look for its soft copy so that people can have it. Look here, the number is here, the numbers are here. Take a screenshot. That is page 208. There's also a number on page 207, one number there. I'm going to go back and give it to you so that you can also have it. Trust me, these are very interesting numbers. They're not obvious numbers. Give them some good thinking. Eh? Number 1 was here. Number 1 and 2, they are here. So have them down also. Take a screenshot for that. This is Bostock. But remember, you have to visit Humphrey. You have to visit also Understanding Mechanics. For Understanding Mechanics, you're going to go to exercise 15A. Do numbers 1 up to 10. Understanding Mechanics, that one you have. Go to exercise 15A, numbers 1 to 7. Eh? Now, I don't know why time does run very fast. Because time does run very fast, there's one other number you can look at here. It's here, I'm bypassing it. Yeah, number 6. Let me do number 6 to finalize with number 6. Number 6 says, when an elastic string of natural length 2 meters is fixed at one end, hangs vertically supporting a particle of mass 4 kg. There is a mass here. At the other end, it stretches to a length of 2.8 meters. So the total length from here up to here has become 2.8 meters. Initially, it was 2 meters somewhere here, as you can see. They are saying, then gradually, a horizontal force of 28 newtons is then applied gradually to the mass until it is once again in equilibrium. They are saying a force of 28 newtons is applied gradually to the mass until it is once again in equilibrium. Calculate the length and inclination to the vertical of the string in this position. So these are the sketches. Okay. So these are the sketches. So if it was initially up, vertically down like this, if I assume it was hanging like this, we have pulled it to the side. Now, what happened when it was put to the side? Do we understand? Have you seen how these illustrations have come out very well? Someone has no question there.
I'm not understanding the second one.
The second one. Now, initially, it was like this. This is the original position. Then what is going to happen is, if this was the original, let me use this one part. This was the original position. If initially it was here, then it was extended by the extension up to here. We are now going to pull it to the side. This was the initial equilibrium line until it comes back to this level. Okay, so we have displaced it away from where it was. So we have retained it back to where it was before by just displacing it upwards. All right, so as we displace it upwards, because we have put a new force that is assisting you to do that, that force is of 28 newtons. there is still an extension embedded in this one. But this extension is not the same as what we had before here, because here we had an extension of what? Why is this very sensitive? Let me have to repeat this one in here. So I was saying if it had come here, we have now displaced it up to here. But as we displace it up to there, there is an extension X. Because now there is a force supporting it, this force of 28, the extension won't be the same as the 0.8 we had before. So this is 2.0. But what does this first extension help us? This first extension, I'm requesting teacher to go back on there. The first extension helps us to see that at equilibrium, when it is not being pulled anymore down, the weight mg, the 4g minus the tension has no resultant force because the system is not moving anywhere. It is just hanging. So with that regard, the sum of upward forces is equal to sum of downward forces. So whenever a body is hanging and it is not falling off, the weight is equal to the tension. If the weight is greater, the body would fall off because it would extend, reach its maximum, reach the breaking point, then the string breaks. But the fact that it's even people who are being hung, someone who has been hanged or who has hung himself, the reason why they are existing up there, it is because the component of their weight is now equal to the tension in the rope. If the body, like a man, like a me, you can't hang me with these funny ropes they used to tie goats, the sisal ropes. No way. With my weight, 100 plus, I put on that cable, it will break. But some of you can be put there, those of you who have 40 kgs. Yeah? So I'm saying here that if the weight is greater, the string will get cut. If it's not getting cut, then at that instant, the tension in the string is equal to the weight of the particle attached. And this is the conclusion for that. So for that, tension, remember, is got from extension out of original length. And the extension in this sense is the original length lambda was not given in the question. So they are guiding you to find lambda. The original length was 2, the extension is 0.8. Then you can make lambda the subject and you get 8g out of 0.8. The 8 comes from bringing this 2 this way. Then you can get the constant of proportionality of modulus, whereby when you divide this by this, the answer is 10g, which is the same as 98 newtons. So that is the reason why they gave you those first cases. Now, in the second case, we are going to see they're asking us for the angle. We have the 2 here. Look at this page and see what exactly is happening. When you look at this page, you realize that, I hope I've explained very well the person who was asking me why it was bent or why it was pushed to the side. Now look here, the modulus of elasticity, where is my modulus of elasticity? So according to this, actually for them, they never wanted to find the modulus of elasticity. Now, when their body has been put to the side, there is a tension of 28. If you remember Lami's theorem, there is a force of the weight of the body, which is 4g. Then there is the tension which is coming from this way. Now the tension here has been reduced. Let me call it T prime. But this T prime, there is an angle up here. Let me assume the angle up here was what? Was theta. If that angle was theta, then this angle here also up is going to be theta. You realize that this is 180 minus theta, whereas this is going to be 90, and then the whole of this one is going to be 90 plus theta. Whereby if you borrow from Lamy, that is why every topic we cover, you must understand. T prime over sine of 90 should be giving us 28 out of sine of theta, should give us 4g out of sine of 90 plus theta. Now people are going to ask me, where does the theta come from? Sine of 180 minus theta is the same as sine of theta. Then sine of 90 plus theta is the same as what? Cos of theta, if you recall. So that is why in the book here they have put cos straight away. That is why here they have put sine straight away. And then this. So with this, you can see that we can merge these two and get 28 out of sine of theta is equal to 4g out of cos of theta, and thus tan of theta can be equal to 28 over 4g. And that is how the theta was got as 35.5. When theta was got, we can find t prime. T prime is going to be equal to 28 out of sine of 35.5, and t prime gives us 48.17, which is given here. But now, because this, okay, we have called it t prime, but here they call it t2. Let's be consistent, let it be t2. Let it be t2. Because this is t2, the first tension was t1, was the tension which I found earlier, this one, let me call it t1. It was 4g, it helped us get lambda. Now, that is why lambda, you see down here, it is 98. They are put here 98. Now, they are looking for the extension. You make x the subject, which will give us 2t2 divided by lambda is our x. So we shall have, this is, remember, our t2. We shall have 2 times 48.17 divided by lambda, which is 98. And then you can get the value of x. But when you get the value of x, the question says, find the length. So you have, because it was inclined like this, and then it had an x here, and it had its 2, they were asking you for the length of the string at that instant, which required you to add the x plus the 2.0. So that's why the answer comes to 2.0 plus 0.98, which was the x. Then you get the answer as that one. Of course, they also ask for the inclination, which we have seen that can be computed from 35.5. So with such illustrations, we should be able to see how they come about. Now, I want to take screenshots of other examples. You try to check them out. In case of any challenge, you get back to my inbox. In case some of them fail to totally come out in your heads, I'll come back in the next lesson and I begin with those examples and I go through them, especially these ones that are coming from Bostock. If I do Bostock and some few of Humphrey, I trust you that you can handle understanding. But if I do understanding alone and you cannot reach Bostock or Humphrey, you can cry very well. So, unless if someone has a question on this number, otherwise our time is running so fast today. I don't know. I don't know why time is very fast today. Who can think of the reason?
Excuse me, teacher.
Yes, please.
Excuse me, teacher.
Yes, please, go ahead.
Need a zeros.
Repeat from X.
Pardon?
Repeat from X how you got the 98.
How I got the 98. The 98 came from here. When you made lambda the subject, this 2 came to 4, then even this 0.8 went down. So it became 4g times 2 divided by 0.8 is equal to lambda, which gave us 8g over 0.8 is lambda. When you divide, you get 10. So it gave us 10g. 10g times 10 times 9.8, you get 98.
From Uganda.
Yes, sir. We are finalizing exactly now. We are just wondering why time came very fast.
Need a sale. What the way they?
Guys, take the screenshot. Watch it. Take the screenshot also for these numbers. Take the screenshot for that number. No, I need to rub off here. The solution is there, so take a look. I will come and give the explanations. Economics is on our case. Also take a screenshot for these two. I'll start from there next time. Mr. Kabagambe, we are once again very sorry. Yeah, Mr. Kabagambe, you came in before 12. Huh? I thought it was even 12, like over past. Guys, take that screenshot and share it. Kyle, let's have a good day.